All right, let's just jump right in. We're going to try and unravel one of the most famous, and let's be honest, one of the most misunderstood ideas in all of science, the truly bizarre story of Schrödinger's cat.
Yeah, how can a cat be both alive and dead at the same time? It's the central paradox, right? The question that just seems to completely break our everyday logic. But stick with me, because by the end of this, you're not only going to understand what it means, but why it points to an even deeper mystery about reality itself.
And believe it or not, to solve this whole mystery, we first need to understand just one single innocent-looking symbol, the plus sign. Yeah, that's right. The whole puzzle really hinges on what plus means. And forget everything you learned in math class. In the quantum world, this simple symbol, it unlocks a whole new possibility that changes everything.
So, first things first, we've got to crack the code of this quantum plus sign. This whole idea is called superposition, and it is the absolute foundation of our entire story.
Our brains are kind of wired for two options, right? A particle is either here or it's there. Simple. But quantum mechanics comes along and insists on this third, totally mind-bending state, this here plus there thing, where somehow it's both at the exact same time.
And look, the perfectly logical question is, doesn't that just mean or, right? Like, the particle is either here or it's there. That's the common sense interpretation. It seems like it's just a fancy way of saying we don't know which of the two spots it's in. But, and this is a big but, that's exactly where common sense leads us completely astray.
And we have proof. The proof comes from one of the most famous, most brilliant experiments ever devised, the two-slit experiment. When you fire quantum particles at a barrier with two slits in it, the result you get is it's undeniable evidence against that simple or idea.
So what's the big deal? Well, the crucial thing is the pattern that shows up on the screen behind the slits. It's an interference pattern. The kind you get when waves ripple and overlap with each other. And here's the kicker. That pattern can only happen if each particle goes through both slits at the same time. It's definitive proof. The particle isn't here or there, it's here and there. That little plus sign, it represents a whole new kind of reality.
Okay, so this is where our story takes a sharp turn, from the tiny world of particles to something a bit more macabre. Back in 1935, a physicist named Erwin Schrödinger took this bizarre quantum rule and basically decided to see just how absurd things could get if you applied it to the real world.
Now, he wasn't trying to prove this was real. Actually, it was the complete opposite. He created this famous thought experiment to show his colleagues, hey guys, if you take superposition literally for big things, you end up with a conclusion that is, and these are his own words, quite ridiculous.
So let's walk through his diabolical device. First, you take a single radioactive atom and put it in a box. Second, if that atom decays, which is a totally random quantum event, a Geiger counter next to it will click. Third, that click triggers a hammer to be released. And finally, the hammer falls and shatters a little flask of poison. So, suddenly, the fate of a poor, unsuspecting cat in the box is directly tied to the quantum state of one single atom. And here's the punchline. According to the quantum rules we just talked about, after an hour, that atom is in a superposition. It's both decayed plus not decayed. And because the cat's life is directly linked to that atom, well, the cat must also be in a superposition, a state of dead plus alive. Schrödinger said the cat would be, and I quote, mixed or smeared out into a state of being both dead and alive. Ridiculous, right?
But here's the amazing twist. The solution to this whole paradox, it was actually introduced in the very same paper by Schrödinger himself. It's a concept that he personally named, and you've probably heard of it, it's called entanglement.
So what is entanglement? Well, it's this bizarre quantum phenomenon where the fates of two or more particles get linked up. Their destinies are intertwined. You can't even describe one without describing the other. They effectively become one single system, even if they're light years apart.
So this brings us right back to the central question. If the theory says this bizarre alive and dead state can exist, why don't we ever see it? Why, in our everyday lives, do we only ever find cats that are very definitively alive or very definitively dead?
Because, and this is so cool, the moment we look, the moment we open that box to check on the cat, that's not a passive act. In that instant, we, the observer, become entangled with what's inside the box. We become part of the very same quantum system.
So the theory doesn't actually predict that you will see a zombie cat, half dead and half alive. No, it predicts a much larger entangled superposition, a combined state. There's one branch of reality where it's an alive cat and a glad you, and there's another branch where it's a dead cat and a sad you. From your perspective, inside the system, there's no paradox. You're just either glad the cat is alive or sad that it's dead. You never experience the superposition because you are part of it.
So entanglement beautifully resolves the paradox for the person opening the box, but it does so at a pretty terrible cost. It rips open a far deeper, far more fundamental problem that lies at the very heart of physics, and that is the measurement problem.
You see, deep down, quantum mechanics has two completely contradictory laws. Law number one is the famous Schrödinger equation. It says that quantum systems evolve smoothly, predictably. Everything just unfolds like a perfect wave. But then you have law number two, often called the projection postulate. And it says that the moment we measure something, that smooth evolution gets violently and randomly interrupted. Reality just collapses and snaps to one single outcome. These two laws, they don't just disagree, they describe two completely different kinds of universe.
And this is the huge, profound question that physicists are still fiercely debating. What counts as a measurement? Where's the magic line? Is it when the Geiger counter clicks? Is it when a human looks? And why? Why does this act force the universe to ditch that beautiful wave of all possibilities and suddenly gamble everything on one random outcome? As of today, there is still no universally accepted answer.
But here's the thing. Don't think for a second this is just some old philosophical debate. Schrödinger's ridiculous case has, against all odds, leaped off the pages of thought experiments and landed smack in the middle of real-world, cutting-edge labs.
I mean, just look at this journey. For 40 years, the cat was mostly a curiosity. The original paper was barely even cited. But fast forward to today, and it's an absolute cornerstone of experimental physics. That same paper gets cited hundreds of times a year now, not by philosophers, but by physicists who are actually building quantum systems in their labs.
So when scientists today talk about making a Schrödinger cat state, they are not talking about actual cats, thankfully. What they mean is taking a macroscopic object, something way bigger than a single particle, isolating it perfectly from its environment, and then coaxing it into a superposition of two different states. They've managed to do this with things like single atoms and even pretty large molecules. The big challenge now is just to scale it up. And why bother? Well, because mastering these cat states is a crucial step toward building powerful, fault-tolerant quantum computers. The same weirdness that puts a cat in two states at once is the key to making the robust qubits that would power a whole new computational revolution.
So what's the next frontier? Well, scientists are now developing experiments to try and create a quantum superposition of a living virus, something that's arguably alive. Schrödinger's ridiculous case isn't just a puzzle anymore. It's a roadmap. It's pushing us to explore the very boundary of reality itself, and it forces us to keep asking that fundamental question: just how far does the quantum weirdness go?